All right. So we're going to venture into chapter 6. So for the next 2 weeks, we'll be talking about chapter 6. What's chapter 6 all about? This is about matrix algebra. Okay. So chapter 5 was maybe just normal algebra. It was just algebra. Now we're moving into chapter 6, which will be matrix algebra. So what does that mean, matrix algebra? Well, here's what it means. In chapter 5, what did we do? We dealt with equations and systems of equations. So we dealt with things like, this. Maybe I'll put some actual numbers in here. So M and B. Doesn't really matter. Point is, we dealt with things like this kind of equation, where I have numbers and I have variables, and the variables just represent numbers. So I just treat the variables like numbers. I can multiply and add the variables. I can multiply them by numbers. I could subtract. I could divide, all that stuff, right? And I could put this equal sign in here to make a statement. So when I make an equation, I'm really just making a statement, a mathematical statement. I'm saying y equals 2x plus 3. And the idea of solving this equation is to find values for x and y that make this a true statement. I could pick values that make this a false statement, but I want to make it a true statement, and that's what solving it means. And then we expanded that a little bit last chapter by doing systems of equations, where I just take a bunch of these, stick them together, and I say I want to solve the system by finding the values for the variables that make all of the equations true at the same time, right? So that's what we did in chapter 5. It was all just equations with variables and numbers, and the variables were treated like numbers. Okay. What we like to do in this chapter is sort of expand that idea into the world of matrices. So we introduced matrices last chapter as a tool to solve systems of equations. We're going to expand on this tool a little bit and sort of flesh it out some more. We're going to make up some properties of matrices that allow us to add them together, subtract them, multiply them, and sort of divide them to get new matrices. So if I give you two matrices, maybe we could add them together to get a new matrix in some way. Or maybe we can multiply them to get a new matrix, something like that. That's what we're going to discuss in this chapter here. And in the end, we're going to end up solving equations like this. Maybe. I don't know. Here's an equation where now everything in this equation is not a number, but is a matrix. Yeah? Everything is a matrix. We want to be able to write down equations where instead of just numbers and variables that represent other numbers, I have these sort of variables and numbers and such that are all matrices. Everything in here is a matrix. A is a matrix, X is a matrix, B is a matrix, and so forth. 0 represents a special kind of matrix. We'll talk about that. So we just need to make sense of all of the pieces here. What's it mean to add two matrices? What's it mean to multiply two matrices? I mean, what's equals even mean in the world of matrices? We have to figure all of that out so that we can make any sense of this at all. So that's what we're going to do. And all of this will be really helpful later on in the course when we get to chapter 8. We're going to solve problems in probability that we couldn't solve before by using this matrix algebra. And something else that we're going to do in this chapter is recast solutions of systems of equations in this kind of format here, using matrix equations instead. So we're going to make everything, we're going to take everything we did in chapter 5 and turn it into matrix algebra. And it'll be very helpful for us. So there's my quick motivation for where we're going. So let's get into the nitty-gritty of it. Start talking about this. So the first thing I want to talk about is, go ahead and erase this, is the first thing we should talk about is the dimension of a matrix. We've touched on this before when I talked about rows and columns. I just want to make it really explicit because I'm going to talk about dimension a lot in this chapter. So what's the dimension of a matrix? Well, the dimension is just sort of how many rows and columns there are. So this is just how many rows and columns a matrix has. That's sort of the dimension of a matrix. And we write it in a specific way. We represent it this way, m by n. So I would read this out loud as m by n. And by convention, this first number always represents the number of rows, and the second one represents the number of columns. Okay. So when I speak of the dimension of a matrix, I'm going to say things like a 2x3 matrix or a 4x6 matrix or something. The first number represents the number of rows, and the second number represents the number of columns. We're going to use this terminology all the time, so it's good to get familiar with it now. So here's a quick example of a matrix. 1, 2, 3, 5, 6, 8, 9. Here's a matrix. What's the dimension of this matrix? How would I describe it? Well, there are 3 rows and 3 columns. So this is a 3x3 matrix. Okay. That's the dimension. Maybe another example to throw on the board would be like, here's another matrix. Again, if I wanted to describe the dimension of this matrix, I have 2 rows, and I have 5 columns. This is a 2x5 matrix. Okay, I could write more examples, but I think 2 is good to describe the dimension. Again, just rows by columns. Okay. This is terminology that we'll use throughout this entire, basically the rest of the course. Okay. Now, the next thing I should talk about, I'm sort of getting out of the way some of this notation and terminology that we're going to use. So this was dimension. There's one more thing I want to talk about, which is another way to sort of express a matrix. That's going to be helpful for me with some of the definitions that are coming. So here's another way. How do I want to describe this? I mean, it's another way to write a matrix. It's maybe a more abstract way to write down a matrix is what I'm about to show you. You know, so far when I write down a matrix, I just literally write down the matrix, right? I write my little brackets and I tell you what all the entries are. And there we go, I just show you the matrix. And that's great, and whenever I could do that, I will try to do that, of course. But there's one other way that's sort of abstract to describe the entries of a matrix. And I'm going to explain that to you now, and it'll be helpful when I give you some definitions of like addition or multiplication, just to be formal with you. So let me show you. Suppose A is a matrix. So I have some matrix, and I'm just going to call it A. A is its name. So I have a matrix A. That's all I know. It's some matrix. Then I can write the following. A equals little bracket Aij. So this is a little a with a little ij inside of square brackets. This means that the entry of A in the ith row, I'll give you an example because this is going to be kind of abstract. In the ith row in jth column is Aij. So the Aij's are numbers. They're the entries of the matrix. And I'm just basically labeling them by which row and which column they're in. So I represents the row they're in, and J represents the column that they're in. So if you're Aij, that means you're the entry in the ith row in the jth column. So if you were A2, 3, you would be in the second row and third column. Okay. So this is a sort of an abstract thing, and I'm only going to use it when I make some definitions, which I'll then give you examples, so hopefully that'll help you get a better feel for things. But I just kind of want to expose you to this because, one, your book will use it if you look in the book. Probably in the finite show this comes up, and I may use it from time to time on the board just as a shorthand for a matrix. So when I write A equals square bracket Aij, I'm just saying that A is the matrix whose entries are represented by the Aij's, where Aij is the number that is in the ith row and jth column. Okay, let's see some examples of this just to make it clear. Let's say A is this matrix. 1, 2, 3, 4, 5, 6. Okay. A is this matrix. I have 2 rows and 3 columns. So this is a 2x3 matrix. And what would be A11? A11 for A, well, the 1, 1 says go to first row, first column. Well, that's first row, first column. That's 1 in this corner here. So A11 is 1. A23 tells me to go to the second row and the third column. So I go to second row and I go to third column. That's 6. Maybe I'll do one more. How about A31? This would tell me to go to third. Oh, no, sorry. That won't make sense in this matrix because the first thing is a row. I only have 2 rows. So how about A21? Now it'll make sense. I'll go to the second row and the first column. That's 4. Okay. And I could keep going. There's 3 more of these we could find, but I think maybe I've made my point. I don't know. Again, the first number represents the row and the second number represents the column. Okay. This is just a sort of an abstract shorthand for the entries of a matrix. Okay. Cool. So I think I have my terminology out of the way, my basic notation and terminology. So we can start talking about the actual matrix algebra now. And the first thing we're going to have to talk about is the most basic thing, which is equality. We have to talk about equals. So let's do equality of matrices. If I want to be able to write equations, I have to know what equals means. So let's just talk about that. So in the case of numbers, back in number land, you know, what does this mean for us? If I write x equals a number, I don't know, instead of a, let's use like 2. What does this mean? What does equals mean and back when we do number equations? Well, this just means x literally is 2, right? Equals just means is the same as, if you will. So we're saying, when I write this, I'm saying x is the same as 2. Okay. We maybe don't think about that too often. We kind of take it for granted because, I mean, it's equals, but we should think about what it really means. It just means that these are the same thing. X and 2 are the same. X literally is 2. So what should equals mean for matrices? Suppose A and B are matrices. What does A equals B mean? What does it mean that these 2 matrices are equal if I write this? What do we want it to mean, probably? I probably want it to mean that A and B are the same. Yeah, they're the same matrix. And that's fine. We could almost just take that as our definition, but let's just think for a second about what that really means. What does it mean for them to be the same matrix? I give you 2 matrices. How do you know if they're the same or not? How would you tell them apart? Maybe that seems like a silly question, but let's just be, you know, let's split some hairs. Let's make sure we write this down and understand when are 2 matrices the same or when are they different. And I claim this is when 2 matrices are equal. So A equals B when maybe 2 things happen. 1, they have the same dimensions. So maybe I want my matrices to be the same size, right? They should have the same number of rows and the same number of columns. So they have the same dimensions. You know, if I have one matrix has 3 rows and the other one has 5 rows, I probably don't want to call those matrices the same because they have a different size, so they're going to look different anyway. So I'm going to ask that their dimensions be the same. And then the other thing that I want to ask is that, well, if they're the same size, they have the same dimension, the next thing I want to ask is that they have the same stuff in them, right? They should have the same entries. So then one way I could word this is corresponding entries are equal. Meaning they're the same size. So I could go to the first matrix and I could go to an entry. I could go to, I don't know, the second row and the third column. And I could go to the second row and the third column in the other matrix, and I could ask if those numbers are the same or not. And if they're different, then these matrices aren't the same. But if they're the same, no matter which entries I pick out correspondingly, then they have to be the same matrix. If I wanted to say this in the abstract way, if A equals Aij and B equals Bij,